All right, let's continue with understanding the propulsion force during cycling. And we are on part 2. And in part 1, we solved for F chain. And we're going to need that equation in just a bit. In part 2, we need to know that chain force, and we need to pick up here. Okay? F chain magnitude here will be the same as the magnitude of F chain here, pulling on the rear cassette. As long as we're not having any stretching in the chain here, which the chain is pretty rigid, so we're okay with that assumption. But that is something to keep in mind, that chains do get worn, and we may actually lose some force between this point and this point because there's lots of movement within the chain, and that's a bad thing. Okay, so let's continue with part 2. And what we're working towards is understanding the propulsion force acting on the bike rider system. All right, so now, here's our drive chain picture. And we're going to do the same exercise we did in part 1, and we're going to identify what torques are acting about the axis of rotation. In this case, the axis of rotation is the axis of the hub. All right, well, I've already drawn the forces, so now let's just identify the torques. Hopefully you can see there's going to be 2 torques acting here. One due to this chain pulling on the rear cassette, okay? That chain, which is coming all the way from this person pushing on the pedal, ultimately over here, is pulling on the rear cassette, tending to rotate the wheel in this direction. So torque due to the chain. Now notice this is part 2. All right, so this torque is also equal to the magnitude of the chain force, which we found out in part 1. It's the same magnitude, times d perpendicular. And I'm going to put rear cassette here. Just a cassette. Oh gosh, is it 2 S's and 2 T's? Rear cassette, the rear gear, okay? In this case, that d perpendicular is this d perpendicular right here. It's the diameter of the gear in the back. D perpendicular rear, oh, I better put rear gear. Sorry, and I'm going to change this here. Just to be consistent, I'm going to put rear gear here. Sometimes I get ahead of myself. This D perpendicular rear gear. All right, now we've got our torque. We've got to identify the direction of the torque. Counterclockwise is positive as our reference frame. If this force were acting from that axis, and this is the only torque acting on the system, it would tend to rotate in the clockwise direction. Therefore, this is a negative torque. Remember, this is part 2. Put aside part 1, okay? What other torque do we have here? We have torque due to the propulsion force. That's equal to the magnitude of the propulsion force times the moment arm of the propulsion force. Where's the moment arm? Well, perpendicular distance between line of application and axis of rotation, right there. D perpendicular, the length of this is D perpendicular of the propulsion force. That's the diameter of the wheel. We can measure that. Radius of the wheel. What direction will this torque have? Well, this will tend to rotate in this direction. If this were the only torque acting on the system, that's counterclockwise. Therefore, that's a positive torque. Okay, that's it. Those are the only 2 torques acting on the system. And now we've identified them. Now we put those torques into the equation. Sum of torques equals I alpha. Remember, alpha equals 0 radians per second squared. That's the situation we're dealing with. constant angular velocity of the pedals. Therefore, because the chain is rigid and the gears are rigid, the wheel will spin in a constant angular velocity, and that is 0 angular acceleration. Therefore, the sum of torques goes 0 Newton meters. What torques do we have acting on the system? We have torque due to propulsion plus torque due to the chain from part 2. That equals 0 Newton meters. We should rewrite this. Torque due to propulsion equals torque due to the chain. Now I'm going to rewrite this again. F propulsion, which is what we really want to figure out here, times D perpendicular propulsion equals F chain times D perpendicular rear gear. That's the size of the rear gear. And remember from our bike anatomy, we can have a gear that has only 11 teeth. That's going to have a smaller radius than a gear with 28 teeth. And the number of teeth describes how big that gear is. The smaller the gear, the smaller number of the teeth, the smaller the D perpendicular of the rear gear. All right, now I'm going to rewrite this with F propulsion by itself. This is what we want to find out. Equals all this stuff, F chain, F chain times D perpendicular rear gear divided by D perpendicular propulsion. All right, now we're getting really close. Let's see, where's my part 1? Pretty close here, but I want to replace this because ultimately what I talked about is I really want to figure out the relationship between what the person is doing and this propulsion force. So I don't have this force in my equation yet, but I really do because we did part 1. So here's part 1, and the result of part 1 was this equation, F chain equals F person, D perpendicular crank, D perpendicular chain. There's our force right there. So what I'm going to do is I'm going to take this part, substitute it for F chain, because this is the same force, okay? This is the same force right here. All right, so it's going to be a little bit of algebra right now, but let me put it in, and then I'm going to do some rearrangement. So F propulsion equals, now I'm going to take part 1, F person. This is going to look a little ugly, but that's okay, times D perpendicular crank. Okay, divided by D perpendicular chain. That's all from part 1, okay? Times D perpendicular rear gear from right here. Divided by, all divided by D perpendicular propulsion. And this is the wheel diameter, or excuse me, wheel radius. Okay, so I need to do a little bit of algebra here, because this is just looking a little ugly right here. This is too much of a hassle. Okay, so what do we do? Well, we've got to do a little bit more algebra. Just remember, if we have a fraction divided by a fraction, what we really do is we flip the denominator, we do the inverse, and we do that math, okay? That's our algebra, okay? So just remember, that's a little tip that we need to do here. We've got a fraction over a fraction. All right, so let's do our algebra. And let me do it. I'll do it the long way. F propulsion equals F person times D perpendicular crank over D perpendicular chain times D perpendicular rear gear. That's all in the numerator over D perpendicular propulsion, the wheel size. And I'm just going to make that a fraction by putting the number 1 in the denominator. So now I'm going to multiply the numerator by the inverse of the, I'm going to multiply the numerator times the inverse of the denominator. So you'll see if I flip this over, that'll be 1 over propulsion. So the propulsion will end up in the denominator up here. Okay, so now let me rewrite it. F propulsion equals F person, this is what the person is doing, times D perpendicular crank, that's the length of the crank arm, times D perpendicular rear gear, that's the size of the cog, divided by, let's do it this way, D perpendicular chain, D perpendicular propulsion. Okay, perfect. This is what we want, this equation. Let me just make sure we're all on the same page with these parameters. F person, what the cyclist is doing, pushing on the pedal. D perpendicular crank is the crank arm length, 172.5, 175, whatever. D perpendicular rear gear, rear gear is the size of the rear cog that the chain is wrapped around. D perpendicular chain is the size of the front ring, the front big ring. So for example, e.g. 11 teeth. For example, e.g. 53 teeth. That describes the size of that big ring. And then D perpendicular propulsion is the wheel radius. All right, so those are our parameters. Let's look at this equation a bit. Let me try to write out some important parts here. I'll use a smaller pen. This is our rear gear, our front gear. This is our rear gear. This is wheel size. So this is a constant. This is a constant. And these are our gears. All right, these are our gears. So whatever gear we're in, everything's fixed over here, except for the force of the person pushing on the pedal. And now, this is what, I can't change my crank length while I'm biking. That's what it is, 172.5. I can't change my wheel size, it is what it is. But I can change these two gears. Okay, I can change these two gears. I can change from an 11-tooth gear to maybe a 28-tooth gear by shifting the shift levers. Or I can change from the big ring, the 53-tooth gear, to the 39-tooth gear. Well, what happens for a given force? What happens to the propulsion force based upon our gears that we selected? These are fixed, okay? We're not going to change these. This is what's going to change when we're shifting gears. If I'm at an 11-tooth gear and a 53-tooth gear, we multiply that ratio by the force of the person and we get the propulsion force. 11 divided by 53, even though that's not the correct math here, but the concept, it works. What if we made the rear gear a 32-tooth gear that the chain is on, and we made the front big ring a 30-tooth gear? That'd be 32 divided by 32 times F person. That's going to tell us what a propulsion force is. So the closer these two gears are in size means that the amount of force generated by the person will yield a high propulsion force. Well, what happens if we do it the other way? If I'm in the 11-tooth and the 53-tooth gear, that's a small number. That's almost 0.2. So the amount of force generated by the person is multiplied by 0.2, roughly, which means this is going to be smaller. What does that mean? Well, if I'm at a stoplight, I want to shift into the big gear in the back and the small gear in the front, because when I push on the pedal, that's going to transfer a lot of force to the propulsion force, and that's going to help me get started on the bike. If I'm biking and I'm trying to maintain a high velocity, well, now, if you remember going back to our previous video on gear ratios and gear inches, I want to be in a small gear in the back and a big gear in the front, because for every revolution of the pedal, I have multiple revolutions of the rear wheel, which means for a given cadence, I'll go faster. But if I'm in a small gear in the back and I'm a big gear in the front and I'm at a stoplight and I push on the pedal, I'm not going to be able to generate a lot of propulsion force. This is going to be a smaller number. So if this is this force, if I push on it with 100 newtons and I multiply that times 0.2, given these are constants, this would roughly be 20 newtons. That's smaller. That means it'd be harder to get the bike going if I'm in a small gear in the back and a big gear in front. All right, so this equation really tells us what influence our gears that we choose on our bike, how it transfers the amount of force that we're pushing on the pedal to the propulsion force. The closer these two gears are in size, the more propulsion force will generate for a given force on the pedal. The smaller this gear is relative to this gear, the less propulsion force we can generate, but we'll also be able to rotate the rear wheel multiple times more for a given rotation of the pedal. Therefore, we'll actually we'll have a bigger gear inch, and we'll cover more distance for a given pedal revolution, which means we can go faster. But we're not necessarily pushing on the pedal any harder to go faster. We're just covering more ground with each wheel revolution. All right, so this is our equation for propulsion force, and it tells us how our gear choice influences the amount of propulsion force generated by a person. And this is why it's nice to have a bike with multiple gears. This is why higher-end bikes may have 11 gears in the back or 12 gears in the back. That gives more options for different gear ratios. And when you buy your bike or set your bike up, you do look at what crank length you want. And wheel size is pretty fixed. That's a standard for most bikes, although some bikes will use a smaller wheel, but we'll consider that to be a constant between different bikes. Okay, thank you.